Okay, in today's lecture we are going to study about Curie's law. So first of all, there are two formulas. One is xi equals to del m by del p, and magnetization equals to del f by del p. So see, this F here is Helmholtz free energy, right? Helmholtz free energy. So first of all, what is F? So basically this is Helmholtz free energy. So when an atom in the presence of magnetic field, okay, with angular momentum J is the angular momentum, it has, that means the atom has 2J plus 1 equally spaced energy levels, right? Energy levels. So in a magnetic field, an atom with angular momentum J has 2J plus 1 equally spaced energy levels. And see here, Helmholtz free energy, that means F, is defined by this formula: e to the power minus beta F is equals to sum of jz, that is minus j2 plus j, e to the power minus beta g mu b j z. So see here, g is the g factor. Here g is the g factor, that is defined as g, the function of jls, and that is equal to 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 divided by 2j into j plus 1. Find 2j into j plus 1. If I am multiplying this gjls with gamma, sorry, this mu b, it will be gamma. That means instead of this term, I can simply put gamma. So this equation now become sum of jz equals to minus j to plus j, e to the power minus beta gamma b j z. Fine. Okay, now just expand this term, expand this equation. E to the power minus beta f is equal to this thing. Now just expand it from minus j to plus j. So it will be e to the power minus beta f is equals to e to the power beta gamma b j. How? Now if I am putting instead of jz equals to minus j, it will be minus of minus plus beta gamma b j, right? Now I am putting minus of j minus 1, so it will be e to the power beta gamma b j minus 1. Similarly, if I am putting instead of this minus of j minus 2, it will be beta gamma b j minus 2 up to. Similarly, if I am putting instead of jz, that is j minus 2, it will be e to the power minus beta gamma b j minus 2. Similarly, e to the power minus beta gamma b j minus 1, and the last, when I am putting in the place of j, z equals to plus j, it will be minus beta gamma b j. Okay, So simply you just expand it, and now multiply either side, both in left side and right side, by the term or factor, that is e to the power minus beta f into 1 minus e to the power beta gamma b. Similarly with this factor also, I am multiplying 1 minus e to the power beta gamma b. After doing some simplification, it will be e to the power beta minus beta gamma bj minus e to the power minus beta gamma b j plus 1. And if I am rearranging it, see, if I am rearranging it, I will get e to the power minus beta f is equal to sine hyperbolic beta gamma b j plus 1 divided by 2. Okay, similarly sine hyperbolic beta gamma b divided by 2. So from this equation, if I am taking the anti-log, so it will be minus beta f is equal to log of this thing, this whole thing you have to write in this bracket. And what is the value of f? Now it will be this minus beta will be divided here in the right side with a negative sign, log of this whole thing will be here, right? And we get the value of f. And from this f, by using this formula, see, by using this formula, now I am deriving magnetization m. Okay, so m equals to minus del by del b of f. So now m equals to, see, m equals to minus del f by del b. So it will be n gamma j bj beta gamma bj. Okay, so this bj, this is nothing but bj is known as Brillouin factor. Okay, this bj is known as Brillouin factor. Okay, this whole thing representing the x, that means Brillouin factor is bjx, and x is here, x is equal to beta gamma bj, and n is the number of atoms per unit volume. And what is the value of bjx? This value, so see, bjx is equal to, the formula of bjx is equal to 2j plus 1 divided by 2j cot hyperbolic x 2j plus 1 divided by 2j minus 1 by 2j cot hyperbolic x 1 by 2j. So this is the value of bjx, that is the Brillouin factor. Okay, so in the expansion of cot hyperbolic x, so we can retain terms which are till first order in x, right? So cot hyperbolic x will be that is approximately equals to 1 by x plus x by 3 plus delta of x cube, right? So here we are neglecting the higher power. Here we are neglecting the higher power of x, higher power of x. So see, this is the case arising from small x. Okay, when small magnetic field is applied, then x is equal to, see, what is the value of x? That is beta gamma bj. This is very less than 1. So when this whole thing is very less than 1, then cot hyperbolic x is approximately equals to 1 by x plus x by 3 plus delta of x cube. Okay, and now using this expression, the value of bjx will be approximately j plus 1 divided by 3j into x. Okay, now this is the value of bjx, and now simply just put this value in this expression, that is in the expression of magnetization. So see, it will be m approximately equals to nj. So see, what is the value of m? That is n gamma j bj and beta gamma bj. Okay, see, instead of bj, I am just putting j plus 1 divided by 3j. Okay, instead of this thing, so just put n gamma j. Instead of bj, I am putting j plus 1 divided by 3j. So see, and here also beta is present, so instead of beta I can simply put, beta is equal to 1 by kt, okay, or kbt. So instead of beta I am putting here kbt instead of beta, and here is the one gamma and here another gamma, it will be gamma square. So, and this b is here, j got cancelled, but here another j is present, right? So here it is. So what is the final expression of m? So m will be nj into j plus 1 gamma square b divided by 3 kbt. Okay, this is the final expression of m. And also here the value of gamma, we know the value of gamma is g mu b. If I am putting gamma instead of gamma square, so it will be g square mu b square. So the expression will be m is equal to n g square j plus 1 mu b square b divided by 3 k bt. So this is the expression of magnetization m. And C, the factor or Bohr magneton number is P. Okay, and what is the value of P? G square j into j plus 1 root over under root g square j into j plus 1. So instead of this thing, see, I can simply put P square, right? P square. So what is the expression of magnetization now after putting this value? So it will be n p square mu b square divided by 3 kb b by t. Fine. So this is the expression of magnetization. Now we are finding the value of susceptibility. So susceptibility is nothing, that is del m by del b, right? So it will be n p square mu b square divided by 3 kb 1 by t. So see, this whole thing can be represented by c, and this is c by t. So see, here xi is equal to c by t. So basically this is famously known as Curie's law. This 1 by t dependence in magnetic susceptibility is famously known as Curie's law. Curie's law. And C is known as Curie constant. This whole thing is C. C is Curie's constant. Okay. So case 2 is when I am considering a large magnetic field. Large magnetic field. That means B is so large, so the value of X, that is beta gamma Bj, the value beta gamma Bj, again for when I am considering the large value of X, So here cot hyperbolic x is approximately equals to 1, and bjx will be 2j plus 1 divided by 2j minus 2j, and this is also equals to 1. So hence for large magnetic field we rewrite the equation, that is the equation of magnetization, as n gamma j, simply n gamma j, because bjx is equal to 1. So instead of bjx I am putting 1, so the expression of magnetization will be n gamma j. And what is the value of gamma? That is g mu b, right? So n g mu b j, and this whole thing can be written like this, ms. Here ms is spontaneous magnetization, spontaneous magnetization, right? So basically this thing, this is, so this ms gives the limiting value for magnetization. And when it happens, now it happens when all the magnetic moments point along the applied field direction. If I am applying my field direction in this direction, so all the magnetic moments, or you can say spin, along the applied field direction. So the maximum magnetization is called basically what? Spontaneous magnetization. This is the maximum magnetization. Okay, this is the maximum magnetization. Fine. So you can also write m is equal to ms bj of x, and the value of x is beta gamma g mu b bj. Here I am putting the value of gamma, and see n gamma j, instead of n gamma j I am putting ms. Ms is the spontaneous magnetization. So the expression of magnetization in the term of spontaneous magnetization will be this. Okay, fine. Okay, the graph will be temperature versus magnetization m. Okay, so this is Curie's 1 by T dependence graph. Curie's 1 by T dependence. Okay, the graph is like this. Okay, so if this is T1 and somewhere this is T2 and this is T3, and here T3 is greater than T2, greater than T1. Okay, so plots for 3 different temperatures, that is T1, T2, T3. So this plot shows the temperature variation of magnetization. Curie's law dependence can easily visible here. So we can say this, you can also say the paramagnetic susceptibility, or you can say magnetization, is opposed by thermal disorder but favored by magnetic field. Okay, fine.